In this lecture, we're going to introduce dynamics, and we're going to look at continuous versus discrete variables, where a continuous variable is one that is a function of t as denoted right here, where t is the continuous variable that represents time. If t is a discrete variable, it takes on integer values from 0, 1, 2, etc., and we denote that using a subscript t on the y. Then we make a distinction between difference equations and differential equations. A difference equation looks at the difference or the change in a variable between two periods. So delta yt is equal to yt plus 1 minus yt for all t's. An example is where the price p, t plus 1 minus pt, is equal to theta pt with theta lying between 0 and 1. So we can rewrite that as the price in the future period is equal to 1 plus theta times the price today. So tomorrow's price will be between today's price and double today's price, given that theta is between 0 and 1. Now we can also look at a money supply situation where the money supply changes from one period to the next according to mt plus 1 minus mt, and it's a function of b, which is the amount that the authority wishes to expand the money supply by each term or each period, and then a function of what the money supply was previously. So it would be alpha times whatever the money supply was in the previous period. Differential equations, there's a change in the variable over time, where time is a continuous variable now. So we define y dot as being equal to dy dt, and that in turn is equal to the limit as delta t changes or approaches 0 as the function yt plus delta t minus yt all divided by delta t. As that delta t approaches 0, we get this continuous time dy dt. So an example would be an instantaneous change in the capital stock, where that is given by k dot, which is equal to dk dt, and it's equal to the investment at time t minus the depreciation of capital stock kt, and delta then is the depreciation factor. Now we want to classify difference equations according to 6 criteria. First order. The first order difference equation is simply one period apart, where yt plus 1 minus yt. A second order equation has 2 periods apart, so yt plus 2 minus yt, for example. An nth order has it where the periods are 9 periods apart. So for an example, yt plus 1 equals 6yt minus 4 is an example of a first order difference equation, whereas yt plus 2 being equal to 3yt plus 1 plus 2yt plus 8, which we can rewrite as yt equals 3yt minus 1 plus 2yt minus 2 plus 8. That's an example of a second order difference equation. Now we can also classify them as to whether or not they're autonomous. In other words, a difference equation is autonomous if it does not depend explicitly on time. So for example, this equation here, where yt plus 1 equals 6yt minus 4 is autonomous because it does not depend explicitly on time. A non-autonomous equation does depend on time in explicit fashion. So for example, yt plus 1 is 6yt plus 5t, and because of this term here, it depends, the yt plus 1 will depend on time when you are in a particular time period. We also classify them according to linear or nonlinear difference equations. Nonlinear, autonomous, first-order difference equations are given by yt plus 1 equals yt squared plus 2, or yt plus 1 equals 2 times log of yt plus 3. Because of the square term here and because of this log term, these are nonlinear equations, but they're autonomous because they don't depend explicitly on time, and they're first order because of yt plus 1 and yt and not a higher order. A linear non-autonomous first order difference equation can be represented by yt plus 1 equals 2yt plus yt plus 1 equals 2yt plus 3t to the cubed, and here we have this term t to the cube, which is a non-autonomous, which makes it non-autonomous. Nonlinear autonomous second order difference equation is given by yt plus 2, that's where the second order comes in, equals 5yt plus 1 plus 2 over yt, and it's because it's divided by yt that this term here makes it a nonlinear equation, and we add this plus 3. We also characterize these equations by solutions. The solution to a difference equation is a function that makes the difference equation true. So for example, yt plus 1 equals 2yt for all t from 0, 1, 2, etc. A solution to this problem is simply yt is equal to 2 to the power t. So if we look at this equation and we expand it, so we look first at t equals 0, then we get y1 equals 2 times we're looking at this here, so it's 2 times yt, and yt is 2 to the power t. T here is 0, so we get a 1. 2 to the power 0 is 1, multiplied by 2 is 2. T equals 1, then we have y2 is 2 times yt, and that we get 2 times y1 is 2 times 2 to the power t. T here is 1, so it's 2 times 2 is 4. And we keep doing this and we get 2, 4, 8, 16. Now if you go back and look just at the left-hand side of these equations, we get that y1 is 2 to the power 1, given by this equation here, and that's equal to 2. y2, 2 to the power 2, is 4. y3 to the cubed is 8, and so on. So you can see that whether we work from the left-hand side or the right-hand side of this solution, we get the same result. Another solution, and this is the thing about difference equations and differential equations, is that you have these more generalized solutions. So yt equals c times 2 to the power t is also a solution, and the solution we had previously, we just had c equal to 1. Now we can also use general notation. So we define an operator e as the value of the variable 1 period later. So then this implies that yt plus 1 equals eyt. Yt plus 2 is equal to eyt plus 1 equals e squared yt, and so on. So yt plus 3 equal to 5yt plus 2 plus 7yt plus 1 minus 15yt plus 10 can be rewritten as, and then completely in brackets, e to the cubed, because of this 3 here, minus 5 e to the 2 e squared, and notice that I've brought the right hand side over to the left hand side, and then we also get the third term minus 7e without raised to the power 1 plus 15, because the minus sign, the 15, and there's no value of the variable 1 period later. So we multiply all that in brackets by yt and set that equal to 10. Now we also distinguish between homogeneous and non-homogeneous equations. And you'll see that this above equation, this equation here, is non-homogeneous because there's a number 10 on the right-hand side. So when the right-hand side is not equal to 0, we have a non-homogeneous equation. If the right-hand side of these difference equations is equal to 0, then we have a homogeneous equation. Now, this is important because later we're going to solve problems and we're going to solve them for homogeneous equations and then later bring in the right-hand side. We can do the same thing for differential equations. We can classify them, but in our case, we're going to only examine ordinary differential equations. We call that, or we denote it using ODE. We do not consider partial differential equations where you have partial derivatives. And although the textbook does discuss them, and some of the material I'm using also discuss them, but we're not going to try and solve those kind of problems. Again, the characteristics we look, or the classifications, we look at order, and the order of a differential equation is determined by the highest order derivative in the equation. So a second order differential equation will look like 3 d squared y over dt squared plus 2 y single dot plus y equals 2, and it's an ordinary or second order differential equation simply because of the double dot up here. And note that the double dot above the y signifies d squared y over dt squared. A third order differential equation is given by d cubed y over dt cubed plus 4 d squared y over dt squared plus 2 times dy dt plus y equals to 2. And notice again, and we'll mention that a bit later down below, that this is a non-homogeneous equation because of the 2 on the right-hand side. Autonomous, again, with differential equations. An autonomous differential equation does not explicitly depend on time. So, for example, if we have y dot plus 5y equals t, that's a non-autonomous ordinary differential equation because of the fact that we have that t there. An autonomous ODE is given by y dot plus 5y equals 3. T does not enter explicitly into the equation. We also distinguish between linear and nonlinear. An ordinary differential equation is nonlinear if it involves any nonlinear terms in any of the y dots, y double dots, etc. So, for example, y dot plus t squared y equals the sine of t is a linear, non-autonomous, because it's a function of t, first order differential equation. Y dot plus y squared equals 2 is a nonlinear, autonomous first order equation, and it's nonlinear because of the y squared. The one above it, this one here, is linear because there is no squared term on either the y dot or the y or any other power to that in that fashion. 4, we look at solutions. A solution is a function that makes the differential equation true. For example, if we have y dot equals b, then one solution is that y as a function of t is equal to bt, but a more general solution would be that yt is equal to bt plus c, and we'd have to calculate what b and c are. General notation that we're going to use for differential equations, we define an operator d as derivative of. So then we have that dy dt is equal to y dot is equal to dy as a function of t, or just that dy dt equals dy if y is clearly a function of time. D squared y over dt squared is represented by 2 dots above the y, and we represent it by d squared y. Then dy dt minus 2y equals 1 is represented by, in brackets, d minus 2 and bracket times yt equals 1. And we can take a more general functional form here, and notice that again, because of the k on the right-hand side that it's non-homogeneous. And we get that this expression can be written in this form: a naught d to the power n, a1 n d to the n minus 1, and so on down. And all of that is multiplied by this term y of t. And again, homogeneous versus non-homogeneous. If the right-hand side in the above equations is not 0, we have a non-homogeneous differential equation. Otherwise, if it is equal to 0, it's homogeneous. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.